What if predicting how a drug moves through the body was like forecasting the weather? Not guessing. Not hoping. Running a physics-based model that has been validated across thousands of observations, and trusting the forecast until local data tells you otherwise. That is exactly how modern monoclonal antibody pharmacokinetics works. And the model has been right for 109 drugs and counting. Every weather forecast starts with the same physics. The Navier-Stokes equations. Conservation of energy. Thermodynamics. These don't change whether you're forecasting in Tokyo or Toronto. The global climate model encodes the physics, and local weather is a specific realization of that physics. Monoclonal antibody pharmacokinetics has its own global model, a two-compartment system with FcRn recycling. Central compartment V1, peripheral compartment V2, connected by intercompartmental clearance Q elimination through proteolytic degradation at rate Cl. FcRn receptors rescue antibodies from degradation, recycling them back into circulation. This model encodes the physics of how every canonical antibody moves through the human body. Just as every weather system obeys thermodynamics, every mAb obeys FcRn-mediated disposition. The global climate model produces baseline forecasts, average temperature, typical pressure, expected precipitation. Climatology. The global mAb model produces its own baselines. Clearance, 0.15 ml per hour per kilogram. Central volume, 46 ml per kilogram. Intercompartmental clearance, 0.27 ml per hour per kilogram. These aren't arbitrary numbers. They were established by Betts and colleagues in 2018 from 27 Pfizer mAbs, then validated across 109 approved antibodies in 2025. They are the climatology of antibody pharmacokinetics. When you hear these numbers, you should feel the same confidence a meteorologist feels reading the global forecast. This is the starting point. This is what normal looks like. 109 weather stations reporting from around the world. Some in deserts, some in rainforests, some in temperate zones. Different environments. Different local conditions. But overlay their temperature patterns and you see the same annual cycle. The same physics producing recognizable, predictable patterns everywhere. 109 approved monoclonal antibodies. Some targeting soluble ligands. Some binding membrane receptors. IgG1, IgG2, IgG for subclasses. Tested in cancer patients, autoimmune patients, healthy volunteers. Different targets. Different diseases. But overlay their concentration time profiles and you see the same bi-exponential decline. The same clearance range. The same volumes. One global model. 109 confirmations. The forecast works. A new weather station comes online in a city that has never been monitored before. It sends 3 days of temperature readings. Can you build a reliable local forecast from 3 data points? Of course not. But you don't start from scratch. The global climate model gives you the expected temperature range for that latitude and season. That's your prior. The 3 days of local data update that prior. Maybe the city sits in a valley, slightly cooler than the global model predicted. The posterior shifts down. As the station accumulates weeks, then months of data, the local readings dominate and the global prior fades into the background. Your new monoclonal antibody just entered phase 1. 3 patients. 6 time points each. 18 data points. You cannot fit a reliable two-compartment model from 18 observations. But you don't have to start from scratch. The platform model gives you informative priors, clearance around 0.15, volume around 46. Your sparse clinical data updates those priors into a posterior estimate for your specific antibody. As more patients enroll, the posterior tightens. The prior matters less. This is model-informed drug development. This is Bayesian forecasting for antibodies. Sometimes the forecast is wrong. A weather station reports temperatures 20 degrees above the global prediction. The meteorologist doesn't ignore it. They don't assume the model is broken everywhere. They investigate locally. Is there a heat island effect? A wildfire nearby? An instrument malfunction? The deviation is informative. It points to something the global model doesn't capture. Some antibodies deviate from the global PK model. Clearance values double or triple the population estimate. The model isn't broken. The antibody is unusual. It has sticky surfaces, charged patches or hydrophobic regions that cause nonspecific binding to cells and tissues. The ACSINS assay measures this stickiness. Score above 11, your station is in a heat island. The forecast needs local correction. You don't throw away the global model. You identify why this antibody deviates and adjust accordingly. The forecast tells you what normal looks like, so you recognize abnormal instantly. In the 1950s, weather forecasts were useless beyond 24 hours. By the 1980s, 5-day forecasts were reliable. Today, 10-day forecasts outperform what 3-day forecasts could do a generation ago. What changed? Not the physics, the same Navier-Stokes equations. Better data. Better models. Better computing. Antibody pharmacokinetics followed the same trajectory. In 2016, Avery proved a transgenic mouse could predict human PK. In 2018, Betts compiled the platform model from 27 mAbs. In 2021, Jamovsek validated allometric scaling across species. In 2025, two things happened. First, the platform model was validated across 109 mAbs. Second, researchers built a physics-informed neural network that predicts PK parameters directly from the amino acid sequence. No animals. No experiments. Just the sequence. The AI learned the same physics the model encodes, FcRn binding, proteolytic clearance, but it learned it from patterns in the protein sequence itself. The forecast is getting sharper every year. 5 forecasting principles. 1. Start with the global model. For any new canonical mAb, your first simulation uses the platform parameters. Don't start from scratch. 2. Check the instruments. Run ACSINS and cross-interaction chromatography before you dose the first animal. If the score is high, your forecast needs correction. 3. Update with local data. Every patient in phase 1 makes your posterior tighter. Use Bayesian estimation, not maximum likelihood from sparse data. 4. Know where the model breaks. Fc-engineered antibodies with YTE or LS mutations bind FcRn differently. Bispecific formats have different geometry. These need modified forecasts, not the standard model. 5. The forecast improves with technology. Sequence-based AI prediction is here. It doesn't replace experiments, but it tells you which experiments are worth running. 1 global model. 109 conformations. The physics of FcRn recycling, proteolytic clearance, and two-compartment disposition. Start with the forecast. Flag the deviations. Update with data. The weather model for monoclonal antibodies has been validated across 3 decades and hundreds of molecules. Your new antibodies forecast is already written. Read it.